arriving, so please be seated.
A very warm and pleasant good morning to one and all present over here, respected guests, distinguished faculty members, participants, a heartfelt welcome to the second and final day of BCCIS 2026 organized by ISTAR, CVM University. It is my proud privilege to welcome you all to this prestigious national level academic gathering.
It is said that knowledge is the only treasure that increases when shared. Today, we stand at the threshold of significant intellectual journey. We are delighted to host the second day of National Seminar on Emerging Trends in Biological, Chemical, Computer and Interdisciplinary Science, that is BCCIS 2026, organized by Institute of Science and Technology for Advanced Studies and Research, ISTAR, the CVM University.
As per our heritage and culture, we shall invoke Almighty's blessing to commence this program. I invite Survi Barot and Tawal Puwar, student of Industrial Chemistry Department ISTAR, to come forward for the prayer. Thank you, Survi Barot and Dholpura.
Now I request Dr. Rohit Dave sir for the welcome speech.
Good morning, all of you. Respected today's expert, Mr. M.R. Gandhi sir, Chief Scientist of CSMC Bhavnagar. Our another expert, Dr. Yatindra Shukla, Director Susuan R&D Center, DDIT Nadia. Respected faculties, participants, and dear friends. So it is a great privilege to have Hello. It is great privilege on this 2 days national conference. We have the eminent personality for this expert talk. So, on behalf of the organizing committee, I welcome Gandhi sir on these occasions. It is a great opportunity for us, all of us, to listen him. He has a very vast experience of more than 40 years in the field of applied science and salt and marine chemicals, and is the personality of such that is traveling internationally and many prestigious organizations of India they are rendering their his service. And this 2 days seminar obviously will encourage the knowledge amongst the all the students, and as a Vidyanagar it is a hub of the education, so all will have a interaction with the various students, faculties and department, so that way you can decide your career and you can develop your thought process, and you will be motivated by interacting and sharing the ideas with others. So it is a great opportunity for all of us. And second lecture also it is all interesting for you based on the nanotechnology. Dr. Yatindra Shukla has also a vast experience in this field. And so welcome all. Welcome Gandhi sir and Dr. Yatindra on this occasion. Thank you very much.
Thank you, sir. Flowers are the sweetest and wonderful things that God ever made. It is a symbol of love and gratitude. Flowers may beckon toward us, but they speak towards heaven and God. So, it is the time to welcome our dignitaries with flowers. Now, I would like to invite Dr. Rohit Dave sir to present bouquet of flowers to Dr. Mahesh Kumar Gandhi sir.
Thank you, sir. Now, I would like to invite Dr. Mayank Patel, sir, to present bouquet of flower to Dr. Atindra Shukla, sir. Thank you, sir. It is an immense pleasure to introduce Dr. Mahesh Gandhi, sir, among you all, who is an ex-chief scientist at CSIS Central Salt and Marine Chemicals Research Institute, Bhavnagar. He holds a BE in chemical engineering and has over 38 years of extensive experience in chemical process development and renewable energy technologies. He is currently working as a consultant for several chemical industries. During his distinguished career, he developed and transferred numerous industrial processes for commercialization in areas such as salt and marine chemicals, zeolite manufacturing, potash recovery, biodiesel production, hydrotalcite synthesis, and value recovery from industrial effluents. He holds 42 patents, including 38 international patents, has published for 24 research papers, delivered 27 invited lectures, and prepared more than 40 technical and project reports. Dr. Gandhi is the recipient of several prestigious awards, including CSIR Technology Award, National Award for Technology Innovation, VASVIK Award, World Intellectual Property Organization Gold Medal, and multiple Dr. Vikram Sarabhai Award for Technology Innovation and Industrial Contribution.
Now the stage is yours, sir. Please join me in welcoming Dr. M.R. Gandhi sir with a round of applause.
Morning to all of you. See many young faces, I've been old. So I don't know. I will have to convey in some lighter way. Because when I was a student, studied at TDIT only, the lectures used to be for 45 minutes. Still it is the same. And in 45 minutes also I used to get tired, and sometimes feel sleepy. See, the title of the lecture, Joy of Invention, is a borrowed title. My colleague and director, Dr. Ghosh, once we were discussing and he was supposed to give a talk in university, I think UDCT. Then he said the audience are students only. So and I said, how about this title, Joy of Invention? And whenever I go to some university and forums like this, I choose this title. I have to acknowledge some colleagues, who participated in the development that I am going to present here. You must thank them. And I will cite a joke on this, There was a fair, Mela. Fair समझते हो? मेला लगा. There were some parrots for sale in cages. So in the first cage, the parrot's cost was written 1 lakh rupee. The guy asked, why it is so expensive, this parrot? Oh, he knows chemistry, he knows physical chemistry, he knows inorganic chemistry, organic chemistry, what not. In the second cage, it was written 2 lakhs of rupees. Why this is so expensive? Oh, he can develop process and his processes are very useful in industry. He can develop mathematical model and whatnot. In the third cage, it was 5 lakhs of rupees, the price. What is so special about this parrot? He said, we don't know his speciality, but the other two calls him a boss. And from that day, my colleagues started me calling a boss instead of my name. So boss don't do anything. He has no speciality. Most of the work is carried out by the subordinate staff, junior colleagues, I would say. And lot of credit is normally earned by the bosses. So that is why I have to thank my colleagues who collaborated in this, and then funding agencies. You all know, faculty knows, fund is very important. Even for organizing this seminar, you must have received fund from somewhere. So I come from CSM CRI, as she introduced, Central Salt and Marine Chemical Research Institute. There you see our old building. This one, Palacious building. This is our new building and instrumentation. Lot of instruments are housed in this building. And here is the chemical department, Alki, Shivar. chemicals derived from that. So it's a chemical science group laboratory, but along with chemicals we also do vegetation. Anything that is done with sea, shore, you get lot of sand there. So silica, zeolite, lead compound, synthetic hydrotelsite, all those chemicals have been developed there. In sea you get lot of algae also, seaweeds. So some chemicals derived from sea, I will show you some of the slides based on this. And instruments are part of, be it a biology, be it a chemistry. You need to have instruments these days to confirm your what exactly you have done and what exactly you have ended with. So CSIR has 38 laboratories. Number is correct, I don't remember now. Before 10 years I got retired. So 38 laboratories and one laboratory minimum in each state. So in Gujarat we have CS and CRI, and like that in Maharashtra you have NCL and many more laboratories, you know. Invention. A good invention actually gives you asymmetrically, improportionally high result, you know. And whatever I am going to talk about today, it is actually inspired by some genuine needs. You need it and you did it. Okay. And not very hi-fi science, because I myself don't know very good science. So something just like we call it street smart ideas. You know, after seeing that, ये तो मैं भी कर सकता था. Yeah. But I didn't try. That is the meaning of street smart ideas, and it should be easy to implement. If somebody says, no, I can't use this mobile, so many functions, so many things to get into. No, it should be very easy to, user friendly, that word you are very familiar with this. User friendly. You should be liking it to use because it is easy. So, that is the thing which we have kept in mind while doing some of the work which I am going to talk about. Salt is very simple, very cheap. You know, you don't give much value while you talk about salt because it's very cheap commodity. Low cost, high volume, some few paisa per kg, no chemical is available at this price. Dirt cheap. But it has enormous amount of applications. Look at the kind of application that salt enjoys. Okay, you think of anything and salt is at the building block, at the base of it. For example, you are very conversant with PTFE these days. Even in the kitchen you have PTFE coated vessels, and in industries you have PTFE coated lines wherever you use acid or chlorine, right? At the base of it, you know, it is salt going all the way through CM1 chemistry up to PTFE, and like that many chemicals like trichloroacetic acid, monochloroacetic acid, some flocculants like polyaluminum chloride and whatnot. Okay, so salt has many end uses. For example, PVC. Everybody has PVC and PVDC in industry and all around, even in the houses, PVC pipelines and whatnot. So salt is a basic building block, then also it is not given that much importance. Why? Because it is produced on the ground. No good big glass line reactor with lot of automation, things like that is not cheap. But salt could have been a very expensive material had it not been using solar energy for evaporation. Think of salt being produced with electricity at the rate of 7.5 rupees per kilowatt hour. Salt would have costed you hell lot of money. So this is the slide I like to show wherever I go. Salt is produced by some people called Agariyas in many parts. This is a photograph of Kharagoda area, Surendranagar district, where 30 lakh tons of salt, 3 million tons of salt is produced. Look at the way they live, look at their lakes, because they move around in the salty crystallizers and even sand, and they have kind of patches on their lakes. And children also live there. They can't go to school and end up becoming agariyas. So, this is the way. So what should be done? At one point of time, these agariya salt people were buying at, say for example, 40 rupees a ton. That is 4 paisa kg. Okay. And because their salt was little bit impure, was not being used in industries those days, and middle people used to take away their salt at 4 paisa per kg. But now, with the intervention, technological intervention, I'll come to this after this. Now, it is being sold at much higher price. I am telling you 10 years back's price 200 rupees a ton kind of thing. That means from 4 paisa to 20 paisa, not much. But now industries are also using their salt. Many innovations have gone round the salt, but I'll talk about only one thing which I think chemically and chemistry is involved in this, much of it. A solvay process, soda ash making process. The soda ash is made using salt. This is the reaction. NaCl, ammonia, water and carbon dioxide gives you sodium bicarbonate. And this NH4Cl is regenerated using lime, slacked lime. Okay? At the end, you get calcium chloride as a effluent. And it is in the stoichiometry. Whatever chlorine salt has released goes as calcium chloride. And most of the calcium chloride at all soda ash factory goes into the sea. They are actually disposing it off into the sea. But in Little Run of Kutch, there is one oldest and first soda ash factory, Dangatra Chemical Works, DCW, you must have heard the name. Their calcium chloride they are discharging onto the land. And that is not allowed. Now, under the new rules of GPCB and CPCB and all that. So, it was proposed to use that calcium chloride into the brine to desulfate the brine. Now, brine doesn't have sulfate. What are the main constituents of the brine? Whether it is from sea or it is from many of the subsoil brines. Okay? Calcium, magnesium, sulfate, chloride, bromine. These are the constituents. But once you remove the sulfate, the salt quality also improves. Salt yield is also improved. Okay? and many trace elements were also found to be lower in that particular salt, and that's how they started getting better revenue for their produce. I'll go back to this just because most of the people who are away from, who are in a landlocked area, they must not be knowing how salt is produced. Like in big cities, the boys are saying they don't know, they know only that milk is coming from the dairy. They have never seen cows or buffaloes or, right? So, like that, salt is produced. See, this is how brine is rooted right from this degree Bombay is again total dissolved salt percentage, you can say. From 3 to 3.5%, it goes on open land like this, they call it circuit in their professional field, and degree Bombay is related to density like this, but it is as good as percentage of total dissolved solid. By the time it comes at around 17 degree Bombay, gypsum gets saturated, it is crystallized out, and at about 25% total strength, salt has come to, it is a fractional crystallization process and energized by sun. And sun doesn't send you the bill. Perhaps my voice is louder than the mic, right? Even if I close this, will do. चालू रखो, ठीक है. So, at 29% concentration, the liquor, mother liquor is discharged from the crystallizer. Why? Because by that time magnesium sulfate has come to the saturation, and it also starts to co-crystallize with it, and salt becomes impure. And this is called beta. And from beta, one can derive many chemicals. All of the bromine produced in India is from beta. It is the only source where from bromine is manufactured. Okay, and many other magnesium chemicals, which perhaps there are some slides on this here. We will look into this. Okay, so this is the salt works of Agarias. Look at this composition. Before this chemical treatment, calcium impurity, this magnesium sulfate and purity was only 97%. But by precipitating, crystallizing out sulfate in form of calcium sulfate, it is 0.09. Many more times, and if some economist is there, he will put the percent which will become manifold, 70% reduction, 80% reduction. But numbers tell that it is 0.42 to 0.09 calcium. Magnesium is also low. But it is good for industrial purpose. For our edible purpose, calcium would have been better, But magnesium is also required by the body, up to 700 micrograms per day or something. And that's why people say, take milk, eat well, vegetables, etc. So for edible purpose, 97% purity would also do a good job. On the contrary, they wash it to remove calcium and magnesium and reduce little bit of sulfate. Then they coat it with silica, and 20 paisa wala salt you will buy in a market at 20 rupees a kg. Or they dissolve the salt, or they take the 25% brine, evaporate in multiple effect evaporator, put some 5 paisa ka iodine, 10 paisa, put some silica. At present I work in silica industry. Through Beautify it, we put talcum powder on this, no? So they put silica on the salt, which is not used by your body. It is not useful in any way. You are spending money on beautifying it or making it free flow just for spending more money. For your body it is not useful. And then you give 20 rupees a kg to that salt. which is produced by 20 paisa in the salt farm, which is more healthier salt than what you are getting in the supermarket. So, as I told you in the earlier slide, that gypsum comes out from 17 to 25 degree Boehme concentration. So gypsum, for 100 tons of salt, some 3 tons of gypsum comes out. Okay, it goes on accumulating after say 3-4 years. The level of the soil comes up because gypsum has deposited there. You dig it out. There are many applications of gypsum. One of them is chirodis that you use in Diwali, right? Second is it is used in bulk in cement industries. Okay, in cement manufacture. Up to 2% cement contains, in one of the constituent of cement is gypsum. Third is plaster of Paris. You must have heard plaster of Paris. Plaster of Paris is nothing but CaSO4 gypsum with 1.5 H2O. Gypsum normally contains 2 H2O as water of hydration. But if you by controlled heat, if you remove half H2O, it has got good strength, and in making false ceiling plaster of Paris is used. But we went still further, better, value addition, they call it. We removed half H2O in the autoclave in presence of water. We autoclaved it with some crystal habit modifier, and then at about 1.5 atmospheric pressure, we cooked it for say 1.5 hours. Filter, dry. The compressive strength of that gypsum, that we now call it alpha plaster, because it is a solution recrystallization process, the rebirth of gypsum. But again contains 1.5 H2O as a water of crystallization, but exhibits strength of 400 plus kg per cm square of strength. So it is as good as that of a cement. So we also develop byproducts like this. 2 industries are using this process. One is in Rajkot, and one of the biggest manufacturer of alpha plaster of Paris. Okay, this is another subject which is Rohit drafted some biodata resume. I like this potash because most of my time I have done this job. Look, every milligram of potash that we use in the country, I would not say is imported, was imported. Okay, that is another genuine need for us to develop a process for recovering potash from beaten, that is mother liquor left out after salt separation. It contains around 2 to 2.5% of potash. Okay, so we can save lot of, and then our country is agriculture country, and NPK, nitrogen, phosphorus and potassium are 3 main nutrition for plants. So, but we are not having K enough. We are not having phosphorus enough, but it was difficult for Brian to get out of it. We have some mines in Udaipur of rock phosphate. So potash was very nearby, was available in the sea, and our soil, majority of our soil, as you see in this, is deficient in potash. All green part, only this pink part is having sufficient potash, But then also, crop after crop, it takes potash. Where from it will be replenished. How to replace this? So potassic fertilizer has to be put in one, and then there are many industrial chemicals like KOH or many industrial chemicals. They use potassium nitrate, heat treatment salt in heat exchangers and furnaces. Where to get it from? Or K2CO3 as catalyst in manufacture of IBB, which is used again. वो आप लगाते हैं ना, what you spray, isobutyl benzene, or when it is a pain you consume ibuprofen. It's basic building block, raw material. They use K2CO3 as a catalyst and sodium metal as a catalyst. Vinati Organic produces this. 70% of market share is enjoyed by Vinati. So, okay, I'll just briefly introduce you what are the forms of potash that we can churn out of bitter. That is the mother liquor of salt industry. 2 to 2.5% potash, but not bad, I tell you. So from bittern, when you evaporate it, and one of the fraction, when the salt concentration is from 32 to 36 degree Bombay, or 34 to be more precise, 34 to 36 degree Bombay, around that, you get one salt in which it is called mixed salt, in which potash is in form of a double compound depending on which brine you had used. Like in which school you studied when you were young. Okay, so it behaves depending on that. If people say if the guy has come from IIT, super intelligent, or if he has come from people like me, TTIT, or you sit for some time, we will ask you later. So, like that, if your bittern contained sulfate, if we had not removed it with calcium chloride, seawater normally contains sulfate, okay, and potash always comes out with magnesium, Mg, as a double compound. If you can't understand this, just don't worry. For years, I also did not understand it. So, but just listen, like, and then you will have like Murari Bapu, I will come once again here, say the same Ramayan. साहब आपने last time भी बताया था, when Professor M.M. Sharma, he was delivering a talk, and Professor Yadav, G.D. Yadav, who was last Vice Chancellor of ICT, it is called now, Indian Chemical Institute of Chemical. Earlier it was UDCT, and Professor Sharma is a big person. Everybody will like to call him, and gives very good lecture, good oratory. But the things are same all the time. It is like Satyanarayan Katha. It never changes. Okay. So, Yadav said that even though he tells same thing again and again, I always go to listen to him. It is a charm to listen to Professor Sharma. And so I was telling my mother that every time there is a sapta, you go there, like that, wherever Professor Sharma's lecture is there, I go and sit down there. Something new will be. So don't worry if you don't understand this. For years I was also not understanding, and I will also show you after this one more difficult diagram. Forget about pehle main nahi samajhta tha. Today also I am finding it difficult to understand that diagram. So if sulfate is there, okay, you get potash there in the form of KCl, MgSO4, 3H2O. K and Mg are good friends. They come out together. But if sulfate is not there, you get potash K in form of KCl MgCl2 something like this. This is called carnallite. This is called kyanite. But kyanite is difficult to handle because one more difficult word I am going to coin here again, put it here again. Kyanite, when you put water, both K and MgSO4 both go together into the water, means solution phase. Okay? They don't separate out. It is called congruent solubility. Congruent solubility. Very difficult word. Don't worry. एक साथ जाता है बस. You know, if Rohit and Atindra were good friends, they go out of the institute together. Like that, and carnallite, KCl and MgCl2 it has got incongruent solubility. MgCl2 पानी में जाता है, but not much of KCl. Understood? So when you put pani on carnallite, you get KCl. But you put water in kyanite, you don't get KCl. On the contrary, there will be some reaction and you end up getting solid phase K2SO4 MgSO4 6H2. And that is this shonite. And what Agrocell is manufacturing as a fertilizer today in Greater Run of Kutch, White Run, आप लोग जाते होंगे, you must have visited White Run on holidays. Narendra Bhai has created a very nice dwelling, holiday homes there, tents and all. That area is Greater Run of Kutch and there are 4 industries where even we never used to see the bird. That area, they are producing shonite just by putting water and removing concomitant NaCl by some physical separation process, you know, flotation, which they are not using, or illustration kind of thing, you can remove NaCl. If you take biton and gypsum together and make it to react, you get one compound called K2SO4 CaSO4 It is called syngenite. Okay, and if you react this syngenite with calcium nitrate, for example, you get potassium nitrate in solution phase and calcium sulfate in solid phase. Automatically got separated. Filter, evaporate, and it is also very value-added potash chem because it has got from here and from this you can get K2SO4 also by chemical manipulation, and then there are processes. Only in phase equilibrium processes you don't have to do much. गरम करो, ठंडा हो जाता है. Okay. Carnallite, as I explained you, it is very simple. Just put water. KCl NaCl mixture comes. KCl NaCl very easy to separate because of their solubility difference in hot and cold condition. It is physical chemistry's phase equilibrium principle. So I will not go much into detail, but if somebody finds difficult, you can ask. Rohit has done PhD on this subject matter. I was telling you, one more diagram I am going to show you, which I find difficult even today to understand. Not understand, but if I have to put a point in this today also, it's difficult for me. I have to catch hold of some young guy who can see that graph paper, small things, I can't even look at it like this. So, why carnallite is having congruent solubility, that thing we are not going into details, but why something gives you less sulfate gives you carnallite type of mixed salt, and why sulfate rich biton gives you kyanite type of biton, This is a diagram one Topman drew it in 1900. Here, 1900, he had got Nobel Prize also. And today, you want to interpret this with all these computers and AI and whatnot, people are finding it difficult because we are not using computer always for study purpose or your mobile also for that. So it is bit difficult to understand. Look at this point one here. It is Dead Sea where there is brine, where there is no sulfate or very low concentration of sulfate. When you evaporate it, it actually ends up in carnellite phase. Okay? Here. Whereas this is sea beton, for example, composition. When you heat up, it ends up in crystallizing kyanite phase. But if you desulfate this beton, okay, you are here then, even better than Dead Sea brine composition. You see the get carnellite. So sulfate is the culprit which actually gives bad quality salt, which also poses problem in winning potash from sea brine, and you get good quality salt after desulfation. This is a composition of mixed salt. When you get a mixed salt after evaporation of beton, KCl is now 20% around, and NaCl is still there, MgSO4 is this, if it is a sea salt, otherwise it will be MgCl2. And this is the composition of beton where it was 2 to 2.5% potash only, and then you go ahead. Okay, case is rough. So, this is late Sri K.C. Shroff, CMD of Excel Industries, you might have heard the name. He belongs to Kutch area. He belonged to Kutch area, and he wanted to do some on that soils, and that was the actually impetus, inspiration that I got to work in Greater Run of Kutch. Okay, and in 80s, I visited Greater Run of Kutch area, and then he said, I am an industrialist. So you produce KNO3, not KCl and things like this. So we prepared KCl from this, just as I told you earlier, with kyanite or shonite, if you react with one nitrate containing compound, it will form calcium sulfate insoluble, potassium nitrate as a soluble species. Evaporate and you get best quality potassium nitrate. It was not a problem, and I demonstrated them the process in my pilot plant. He himself visited this. He is not only an industrialist or philanthropist, but great social worker too. You know, I visited the Run area on his request or with his guidance, not request. And we saw that Run, we know Run as a sand dunes and land of sand and things like this. But what we explored is Run is white covered with salt. What happens here is, this is a satellite imagery. In those days we didn't have mobile. 80s. You know, some of students, younger students must be schooling at that time. So we visited this area. We took satellite imageries from National Remote Sensing Agency, Hyderabad, you know, and this is the one. This is a Kori Creek area. This is a sea. So water inundates in this area during high tide, and because it has got conducive evaporation condition there, it evaporates and forms a natural bed of salt and beton above the salt bed. So profuse quantity of bittern, if you want to delink your potash production or bromine production, but you don't want that much amount of salt to be produced, you can use this, and it's a potential natural source of bittern there. And that's how first built company came up, then Agrocell almost simultaneously. After that, there is one company called Archean Chemical Industry, and all of them are making bromine and potash now. Solaris is taken over by Excel Industries, Agrocell Industries, and in love of those industries, Excel sold out their shares in Excel Industries, and it is Sumitomo Chemical now. This is the area I was talking about in the beginning. We also produced mixed salt and potash and demonstrated it to National Fertilizer Limited. In my curiosity to at least bring couple of potash plants during my journey into the institute, and somehow, unfortunately, by the time I demonstrated and we made MOU, I retired and the plant could not come up. Reasons behind it is internal and not part of any academic discussion. So, but we put a potash plant, demonstration plant, big plant at Mithapur. I got money from DST, Department of Science and Technology, some 15 crore rupees. Very rare to get this much amount of fund, and some another 5-7 crore for putting up a potash plant in our salt farm, Institute Salt Farm. And you look at this, it was inaugurated by Professor Sharma. Again, this is our institute plant, and this is Tata Chemical Mithapur's plant. And I was very happy. It was on my retirement only that these two plants got completed, and retired on a very good note. Okay. There is one more interesting product that can be churned out of. I told you, how carnellite is made. Now, in carnellite, there is always associated salt crystals with the carnellite, because sodium chloride never gets exhausted in the brine. It goes up to end. Okay. So if you put water in the carnellite, MgCl2 goes into water and KCl and NaCl remains in a solid phase. That is a low sodium salt. Many people suffering from hypertension, doctor advised them to take salt less, NaCl. And there is a company called Dabur or Saffola. They make low sodium salt, and people buy it, eat it. But what they do is, they take NaCl and put KCl sourced from outside and mix it well. Whereas we produced a process in which from the same brine at different stage we can get low sodium salt. Okay. And this was given to Hindustan Unilever. You look, demonstration was given in Agrocell Industries, Dordo. This is your bromine plant in Agrocell Industry. These are big ponds in which I am desulfating this, and here I am going to get my carnellite. So this was given to two companies, one to HUL, but HUL never came up because HUL doesn't have its own salt farm. This was demonstrated to HUL in Agrocell premises. So they asked others, they outsourced the salt whenever they were dealing in salt, Annapurna. So they stopped Annapurna by the time low sodium salt comes into the market. And that's how they did not go for this. Okay, I'll come to this slide. This toy is better. Otherwise, I have to finish with this slide as and when it comes. But it takes me forth and back. So I think I'll come back later. Look, this is one concept I am showing you using, and the same concept is used at couple of places now on an industrial scale. In Rajasthan, salt is made from lake brine or subsoil brine, but they don't have calcium, magnesium in their brine. What they have is sulfate only. So sodium sulfate is one of the impurities there. The salt always is contaminated with sodium sulfate, most of the salt. And look, I used to first prepare a saturated brine using sodium sulfate and sodium chloride. You get the saturation solubility of around NaCl 28%, Na2O, Na2SO4 8%. Now you chill that brine. At lower temperature, at 10 degrees, my all sodium sulfate, most of it will come out, and NaCl is a very, very good student. At low temperature, it does not change its solubility. At higher temperature, also it does not change its saturation solubility. So it has same solubility, and that Na2SO4 has crystallized out. With that brine, I am washing my salt to upgrade this salt from 13% to say 2%. Now it is again rich with sulfate, sodium sulfate. I again chill it. It's a cyclic process. But this process is also hooked up. You must have heard there is a near Coimbatore, there is a big water treatment plant. Water that is coming from 750 dyeing industries there. I forgot, DAT, Tirupur. There is a village, a town called Tirupur, where 750 dyeing industries are there. The effluent contains color, and for imparting dye onto the cloth, they have to put all this salt, NaCl or Na2SO4. Now, huge 55 mld, if I remember the capacity correctly now, water treatment plant was installed by government. But at the end, they end up with a mixture of sodium chloride and sodium sulfate. So I hooked up this device, this system there, and now they can separate NaCl and Na2SO4 and use again in their dyeing units, you know. So ZLD kind of, or no effluent, zero effluent kind of thing. This one is very helpful from that point of view. Yeah. After this, I will show you that double fortified salt. Because we are in salt, we work with magnesium. We have love with magnesium. So one thing that occurred in our mind long back, that why don't we produce one compound which was entirely imported in those days, even today, but now only one company is producing it in India with this process, is a magnesium aluminum hydroxycarbonate. Magnesium comes from the beton I will take as raw material. Aluminum, there is lot of hue and cry in Ankleshwar of aluminum chloride, which is used as anhydrous form as a catalyst in Biederkraft reaction, and lot of aluminum chloride used to come out. Nowadays people are actually using it for making polyaluminum chloride, but in those days it was a menace. It was considered to be a menace, you know. People faced closure due to aluminum chloride discharge. So aluminum chloride and magnesium from beton, we developed a process in which magnesium aluminum hydroxide, octahedral, it is layered. But then it has a positive charge. The electrons did not get balanced. Okay, in presence of all this, professor, it's a bit difficult to speak such basic chemistry. But carbonate goes in and balances it. So it's a mobile anion. And wherever it is used as, for example, in polymers for scavenging chlorine. In polymer preparation, there are processes like Ziegler-Natta, wherein acid is used as catalyst. So this contains chlorine, but after some time, if chlorine is not removed right in the root, the plastic becomes brittle or off color and things like this. So it is added as a polymer, it stays there in the polymer, but scavenges, takes chlorine in. Carbonate goes out as CO2. Okay, it is used huge quantity by Reliance. So we developed the process. It is also used as a pharmaceutical ingredient in acidity formulations like Celugil or something like this. And this is the reaction by which it exchanges, you see. Yeah. The chlorine goes in, CO2 out, and this is the kind of presentation of that compound. And there is a company called Ubeck Color Private Limited, belong to one German guy, German-Austrian mixed, Rainer Ubeck. He was very fond of reading patents, and one of the patent on hydrotenside, which was published very early, I don't remember, about 25 years back, he got to read it, and then he told me, he sent his people from you back to this place, CSNCR. We worked out a process for him. All raw materials except biton. Biton is available in plenty near Bharuch. In Jambusar area, I was going as a consultant in many salt works. So there they put up a plant of few tons per day. One of the effluent containing ammonium carbonate coming out from copper phthalocyanine Greek. They use urea as one of the maybe reducing agent or something.
Urea is the main.
And ammonia is released due to this. I don't remember. 10 years back, I saw that. Now it is sold out also. Ubeck is sold out to Sudarshan Chemical. Because they became, after Rainer died, the children enjoyed like me and, you know, this is the Rainer guy. Very powerful person. One of the things which I discussed with him during inauguration, I will tell you in the next slide. Okay. Before that, I'll take you back to that. Yeah. Iron and iodine fortified salt. Iodine fortified, so you people are eating. But in many children, and especially the mother, caring mother, expecting mother, they always have iron deficiency. And many children also have iron deficiency. So salt was chosen as a base carrier. But the problem is, iron is, it was understood at that time, it's a myth that it is only, you tell me the time, because I don't have watch. Still time for me to go? Huh?
Rohit is the boss.
Up to 11:30.
Sir, Rohit is the boss.
Yeah, it is already 11:27. Finished. There's no more stories, huh? So I used that SHT to, instead of magnesium aluminum hydroxy carbonate, I made magnesium iron, Fe plus 3, hydroxy carbonate. All ferric compounds are brown or ferrous compound is greenish. Salt cannot hold this because you will never like to eat that salt which has got dot black particles. કાકરાવાળા ઘઉં નથી ખાતા આપણે. So salt also we want white only. So I use this SHT to replace aluminium with iron, and surprisingly the only iron compound that in Fe plus 3 form was white. And now I can fortify and sell and enjoy, and people also enjoy. And it makes the salt free flow again because it has got magnesium hydroxide and ferric iron, which is not hygroscopic. Very nice. Oh, I will go fast. Not much of things now left also. Zeolite, it looks it is the compound which is as complicated as it looks. It's a frame-like of structure made of aluminium and silicon and oxygen, but here also it is charge is imbalanced. Here it is negative charge, and that's how sodium with here cation goes. In SRT, anion was going there. So this is zeolite. Many uses. The bulk use was in detergent. Why it was used in detergent? In all foreign countries, all advanced countries, nobody is using phosphate as a detergent builder. It is for that purpose it was being used. This is the process. Process is very simple. When it is looked at flowsheet in a diagram, sodium aluminate and sodium silicate are reacted, and sodium aluminate you can make from again effluent AlCl3, but here it was developed for NALCO, where aluminium or alumina is produced, is extracted from bauxite. Bauxite is a very colored compound, rock. You leach it as sodium aluminate. Aluminium is amphoteric, so you get sodium aluminate and then precipitate out. That intermediate liquor is very brown in color, but zeolite is supposed to be white in color. So we developed a process like this, and then compared with whatever international product was there at that time using XRT and SEM, and even from many other rocks, bauxite, leachate liquor. One plant is put up here near Bhuj, Nerdi. So two big plants of zeolite have come through this development. This is the photograph of the plant in Nalco, and this is a much talked about thing for one. Sheikh has also come seeing our progress in biodiesel, thinking that from tomorrow people may stop using diesel. Conventionally used. So he came. We have one very bad habit to do ho karke. Oh, we made the words based biodiesel and things like this. And you know, Daimler Chrysler's Mercedes-Benz car ran on that. Neat biodiesel. So he came all the way using his plane. Then what these guys are doing? Tomorrow I will be put to lot of loss, monetary loss. And he saw this equation is very well known, but I will not go into details. But the novelty of the process that we had developed at that time, all the processes till that time, all they spoke about biodiesel, which is made using methanol and alkali as a catalyst, but at high temperature and for couple of hours together. We made it in few minutes, no temperature, all simple equipment. In my first slide I had said ease of implementation. नहीं चाहिए ये सब, you know, and we made, there was no effluent generated. Everything used during the process, whatever is produced is used for some useful purpose. And these are the things, even some small amount of, after distilling glycerol, we made plastic, biodegradable plastic, you know. These are some of the plants that we put. You see, this is Jatropha seeds actually come as a pod, big pod in which 3 small seeds are encompassed. Now, to do that, we had designed and developed a machine that will bring out the seeds. This is the briquetting machine for this and producing white coal, which can be used in boiler, and many people are using it. This is the plant that we put up in Hyderabad. This is the plant perhaps we put up in Jaipur, Udaipur. The cars were taken to Leh, and all big newspaper printed this, you know, and then there was one small article also in Nature. And that's how that Sheikh Abdullah came and visited us. I said, nothing is there, don't worry. We don't have raw material even to feed our institute. Forget about the whole world. So, and some algae, because I saw your document that it is interdisciplinary, this, that. So I wanted to make some small case studies how we worked interdisciplinary. You know, in all this process, biologists will be there, chemical engineering will be there, chemists will be there. For example, we grew some algae, cultivated, and then I'll not go much into details, but then there were 2 products turned out of it. One is, actually I started late. This is some few overs you have to give me, you know. I started late. Instead of 10, I started at 10:15, you know. So, granted. But I tell you very honestly, next lecture I should not cut off 1 minute also, because it will be very meaningful. Nanoparticle, science of the day, and very contemporary speaker. So when you like sugarcane juice, sardine or us, we churned some juice out of it and then put it in the sugarcane farms and some other cultivation, and surprisingly it gave excellent results as an input, you know. I'll show you this result. See, sugarcane, it yielded juice quantity by 7% more, and its streak size and thickness became big and all that. And the residues, after that churning, whatever were left, we produced alcohol from them, hydrolyzed it, and then fermented it. And you get very good alcohol with which we ran a car. These are some of the results of alcohol that was produced, and you, because Baroda is very close by, Kane, Dr. Kane, you know, perhaps know many of you. He was Vice Chancellor and earlier worked with our institute also as a mechanical engineer long back. So he poured the 10% alcohol, you know. And nowadays in petrol that you are using, we are putting 20%. So that was one thing. And another, this is what I wanted to show you. This is called microalgae. The one which I showed you in the sea, it is macroalgae. This is microalgae even in the house. If there is a water tank on the ground level, and if you don't use it for some time, there will be some algae like this. And in many ponds, you get this. And what did we do? We actually extracted oil from that and made biodiesel also from that. You know, once you are on some track, એને ચડાવી દે કોઈ, then you go on doing it. We will make biodiesel. Algae, we will make alcohol. You know, so this was the biodiesel from algae. We actually, it was done in Delhi. Our minister at that time, he is no more there. He has died. So he had started with B100 again. You know, and fine. This must be the last slide because that was the last thing that I did. You know, if there is a saline land and if water inundates over that time and again, nothing grows there. But there are certain plants. One is this Salicornia, we call it. They grow on such land and with some irrigation with seawater. These are called hallotolerant plants. And then they give seeds, beautiful flower in that season, and seeds which yields oil, which is very good even for eating. And again, line chadavi dida, so we make biodiesel also from that. And another product that we get out of it is salt, because it has taken salt from seawater and sandy dunes. So when we burnt it, and so 40% of salt is there in its structure. And that salt had a beautiful properties for keeping you healthy, you know. And many doctors, we transferred this process to one company who is producing it. Its brand name is Saloni, perhaps. You know, Loni means salt. From that Saloni, and it is sold at a very high price in many markets. So this is what you might have seen here, that anything that we have done with genuine need, and all that what I presented did not have input. Very hi-fi, very ordinary people can do this. Okay, so ease of implementation. So in the first slide, whatever I had said, that it is for ease of implementation, it is very normal, strict, smart idea. I have stuck to it in my presentation. Thank you very much for your patient listening. And I am not here. Or he is little bit farther, because I am a boss. That's not my first. Actual work, though, people like them. Question? Yeah.
First of all, thank you, sir, for your beautiful presentation. And as in my second year of BSc Chemistry at Xavier's, I had been working on, rather, I would say, I had a review article on anemia, but especially the pernicious anemia syndrome. So I was taken up by the slide which you showed that it was published in the newspaper as well. You prepared something, some kind of compound or salt with Fe. So would you please elaborate on that? How did you prepare that? And second question, will that be effective for all kinds of anemia, say vitamin B12 deficiency, folate deficiency, and iron deficiency anemia? So would you please elaborate?
Look, first of all, I will confess that I am not a medical background person, but I'm a chemical engineer. We took this salt, for example, to bark, BARC. There was one lady in pharmacology. She agreed to check my salt containing iron is one of the constituent in the SHT, synthetic hydroxide that I prepare. Okay, and I put it there. Magnesium is also good for health, not bad. Sulfate is also not that bad. Okay, so it was put in, but I was afraid. It is in Fe plus 3 valence. And all medical guys, they publish, and I have read it everywhere that Fe plus 2 is bioavailable. They don't say Fe plus 3 is not bioavailable, but Fe plus 2 is bioavailable. But to my surprise, on Wilmar labs, it was radio labeled iron. My compound was given, and to best of my surprise, it is more bioavailable. Don't tell anybody outside this room, otherwise they will come and beat me at home. Fe plus 3 is more available, bioavailable. And then I did one more wrong thing. My wife always had a very low hemoglobin, and she was suffering from rheumatoid arthritis and whatnot. So doctors always used to give, after seeing her blood report, one iron tablet, Fepol or whatever, Fe plus 2 or. I brought it from the institute, which is a chori. You are not supposed to take, even pen you can take from local. I will come tomorrow and use it again from the same table. I took it in my compound in a house, blended it with salt, and we all started taking that. Kind of a clinical trial. After that, we bought a lot of rats and we did it in medical college also. I'm not detailing all that. But to our amusement, all of us were lal ghum. My wife, who was never more than 8 HB, she was 11. And doctor also said, what are you doing? And there was one guy called Tripathi, Dr. Dean of a medical college. He assigned this project to one of his students, pharmacology MD. We bought a lot of, from Zydus, lot of, okay, ethical studies, they call it, clinical. But we took ethical committee's approval and all. And there also same result, but we did not publish it because we never wanted to come in controversy with medical profession. Because we also have to go someday to them. So it is bioavailable, one thing. In the same form, anybody can use it. I can tell you with confidence, perhaps your question was that only, whether this is bioavailable in this form or not. If I put your question in a small condensed manner, whether it will be made available to the body, to the deceased person, okay, that is what your question was. If you take this iron, you will speak like this loudly. I'm telling you. You won't need mic then. I'm telling you.
Actually, Fe plus 3, when we take it, it has to be converted by body in Fe plus 2. Then only it is absorbed at the gut level.
Who says so? The actual experiment tells me this.
Okay.
And Fe2 is unstable compound. And by La Chatelia's principle, in your system, you are every fraction of second breathing. All cells have oxygen, blood carried to them. So the moment the Fe plus 2, these are my logics, let me tell you. Fe plus 2 gets oxygen, it will get converted. See, system goes towards stability. What is stability? Stability is from that state, it cannot go to another state. From 2, it can go to 3. But 3, after 3, there is a Akasi.
Yes.
I don't know much chemistry and I should not talk. So, you know,
This one, actually, there are many enzymes and compounds in body which will convert Fe2 to Fe3 to Fe2.
Yeah.
Then it will be metabolized, and again at cellular level, what sir said, it will be converted. Cytochrome C is also there, which is doing this cycle, Fe2, Fe3. Your hemoglobin is also capable of doing this cycle. Iron redox conversion to 2 to 3, 3 to 2. So body has an internal mechanism to do this redox chemistry. In any form, if you take iron, either 2 plus or 3 plus, both are bio.
Okay. Yeah. Thank you.
and for engineering, chemical engineering, introduction to chemical engineering, there is a definition. In the first book I had learned, a chemical engineer is nothing more than a joker. He talks chemistry in presence of engineer. He talks engineering in presence of chemist. And he talks politics in presence of both. No. So I said I am not a medical student. I confessed it. Very nice. Very nice.
Yeah. Thank you.
Thank you. I'm getting away. Yes, right. But this
Yes.
Thank you, sir. This sacred flame of joy of invention has inspired us towards knowledge, innovation, and academic excellence.
Thank you, sir, for such an enlightening and thought-provoking lecture. You begin your lecture with a warm and humorous remark. Your talk on the theme, Joy of Invention, was very informative. You beautifully emphasized that true innovation is not about titles and hierarchy, but about contribution. The concept that meaningfully inventions create asymmetrical gains and must emerge from genuine need, be user-friendly, ease of implementation, and guided by street smart thinking was both practical and motivating. Your explanation of the fundamental role of salt as building block of many chemicals like fertilizer from salt water and other examples was microalgae to make biodiesel. At the same time, your light-hearted humor throughout the session kept it engaging and reminded us that learning and joy can go hand in hand just as your topic.
Now, I am delighted to introduce Dr. Atindra Shukla among you all. Sir is an associate professor. Sir is associate professor.
As a token of love and respect, I would like to invite Dr. Rohit Dave sir to present memento to Dr. Mahesh Kumar sir. Gandhi sir. Thank you, sir. Now we have a 5-minute break.
Director Bhatta.
Now, I am delighted to introduce Dr. Atindra Shukla among you all. Sir is Associate Professor and Director of SAS Kalman Center for Surface Science and Nanotechnology, Department of Chemical Engineering, Dharamsir Desai University, Nadia. He holds a PhD in chemistry and has completed postdoctoral research at the Weizmann Institute of Science, Israel, and at the University of Miami, USA. He also served as scientist at CSIR, Central Salt and Marine Chemical Research Institute, before joining academia. With over 2 decades of teaching and research experience, his expertise lies in nanomaterial, surface science, smart materials, and advanced material synthesis. He has published more than 70 international research papers, authored book chapters, hold 5 patents, and has an H index of 26 with over 2100 citations. He has guided multiple PhD scholars and continued to actively mentor research students. He is a recipient of Young Scientist Award and has contributed significantly to academic, leadership, and research development. Please join me in welcoming Dr. Atindra Shukla sir with a round of applause.
Am I audible? So, previous lecture was delivering is my good, and even Dr. Rohit Dave. So my PhD journey, actual research career started from CSNCRI Bhavna, and at that time he was in charge director and senior most scientist after the director. His role was to develop the processes. So he showed many of the processes. Some of them were, as rightly pointed out by him, that they were not developed by him, the inventions. But yes, process optimization, scaling up, making it commercially viable, all those things were done by Gandhi sir. So that is why you saw the correct display of interdisciplinary aspect of science and technology. And yes, if you see the history of science and technology previously, there were not too many branches. It was not compartmentalized like today it is. Slowly, when you grow, when you climb up the ladder in research and enter into some specific field of research, you slowly start finding out that again, everything science and technology is one. You don't need compartmentalization. And this is one topic where again interdisciplinarity of science and technology will be exhibited very in a very profound way. So that is what we are going to for this. So we are listening or hearing about nanomaterials since last couple of decades now. But if we compare with the scientific advancement in the last millennia, this is very new topic relatively, particularly the nanomaterials. But that doesn't mean that they were not known. Now they are. Now we are able to, or they are visible to us, and we can visualize at their scale, and we can magnify, we can see their morphology, we can see their shapes, what is there on their surfaces, all those things are now revealed slowly in a better way. So that is why nanomaterials are becoming more and more popular. And as the time grows and R&D getting mature, the nanomaterial applications are also becoming wider, and it is covering almost all the aspects in the life. So basically this is a Greek word nano, means dwarf, tiny, and that is basically dealing with 1 nanometer 200 nanometer scale materials. Larger than 100 nanometers, then you can call it nanomaterials, but they are normally uh, measured as point something micron. So if it is smaller than 100 nanometer, then normally people don't call it zero point 0.1 micron, but then they call it 100 nanometers. So that range, 1 nanometer to 100 nanometer, that is mostly what we call the nanomaterials. So here the size comparison chart is there. 1 millimeter, 1 meter, then 100 millimeter, 10 millimeter. So tip of a pen, pin, the કાચની આપણે જેને ગુજરાતીમાં, that is 1 millimeter. Then 100 micron. Our blood cells are 10 micron, so they are actually in microscope. You can easily visualize that. Then we go below 1 micron. There, some of the instrumentation was not capable, so it hit the limit of the instrumentation there. And then onwards, 100 nanometer to 1 angstrom in this scale. 1 angstrom is basically 0.1 nanometer. So 1/10 of a nanometer, that is angstrom, is almost at the atomic scale. So DNA molecule is a macromolecule. It is made up of lots of organic building blocks. But again, it is in the range of 1 to 10 nanometer. So DNA, when you draw the structure and if we see the components and all the building blocks and all, it is looking like a very large molecule, and by drawing someone would think that it is a very large molecule, but dimension wise it is still a nano material. So these are all the nanomaterials, and some of them are these. We can see here it is better comparison natural nanomaterials or natural materials as per the scale, and man-made. So these are man-made materials which we made in a particular nanoscale, and these are already naturally existing. So advancement of the instrumentation, particularly to identify and study the nanomaterials, has helped us in getting the information about this thing also at the nanometer scale or even beyond. So there are techniques, some of them we will cover in the last part of my talk, where the techniques related to nanomaterials characterization or some studies if we want to carry out nanomaterials can be done. So this is a human hair, which is 100 micron size, and these are the nanofibers. So human hair is almost like a big cable, heavy cable, the electricity wire actor, like that looks like compared to Pagana Dora. That much scale difference you see with nanofiber versus hair. So when nanofibers are generated, and there are many techniques for generating nanofibers. One is electrospinning. Some of you might have read about it, and it is available in this region, not in this university, but in Charusai. So electrospinning, you can produce nanofibers, and that nanofibers. Now nanofibers, when you look at nanofibers, if I make 1 gram of nanofibers and fill in the water, if I show it to you, it will look like just a powder. Then you will not be able to term it is nanofiber or not. That will be seen only when we put it in an electron microscope, and then scanning electron microscope will show you this type of structure for this fiber. Otherwise, it will look like a common powders. If it is white color, then it will be white powder. If they are carbon-based nanofiber, then it would be black powder. So it would be looking completely black. If you give activated charcoal also in place of nanofiber, you will not be able to distinguish unless you see them at this scale. So that is why nanomaterials might be existing in past. Some of their effects also were exhibited or studied in past, but at that time there were not enough techniques available to identify them clearly and pinpoint the relation of this effect with those materials. So that is why, so nano world is basically in the 1 to 100 nanometer range, and there we can control and manipulate the matter at the atomic or molecular level. So if you control the matter at the atomic level, it is even beyond nano. So nowadays world is moving very quickly to the level that is called beyond nano, means at angstrom scale. But normally at molecular level we can control many things. If many of you if are from the chemistry background, we can design or alter the molecule at the molecular level. Like we can attach a new part into, we can give a new functional group. Through functional group, we can attach a new molecule. Say, for example, if you have a carboxylic acid group, we can convert it into amide, and to amide we can attach anything else. So, like that, we can build a molecule and we can control the matter or material which is final resultant material at the molecular level. And sometimes if we are able using various specialized technique, we can control at the even atomic level also. If we start at the atom level, certain vapor deposition and ablation based techniques, we can go up to even atomic levels also. So that is basically nano world. And previously, about 20 years back, very high amount of research world started, particularly the developed countries. So this is an example from the National Science Foundation. In their meeting, they reported that nanomaterials are such materials which can be controlled at the nano scale in terms of their properties and their functions. So that Nanoscience and Technology Council they made. This was made by NSF. So National Science Foundation is the USA's science research agency, just like DST we have. They have NSF, and NSF is normally not divided like ours into DBT, DST. So we have lots of division in science and technology agencies. There it is single NSF. It runs space programs also, chemistry also, defense research. They have a separate agency, but otherwise majority of the programs NSF runs. And NSF has created Nanoscience and Technology Council in 2000. And there they started looking into that, and that time while making this council, they had made a statement that nanoscience will change the nature of almost every human-made object in the next century. And we passed about 25 years, so quarter of a century is passed, and we are already seeing that it is happening. So this has become almost a prophetic statement that by the years passing, we will see more and more dominance of nanomaterials or nanoscience and technology, altering the human-made objects. So these are the year-wise breakthrough for nanomaterials. As I said, that Nano Science and Technology Council in USA was made in 2000, but that doesn't mean that R&D started there onwards. It was already going on. So semiconductor quantum wells were reported in 1980. Then scanning tunneling microscope, it is an instrument which can go up to molecular and sometimes even up to atomic level. So that instrument was made, and it enabled the atomic scale imaging. And then fullerenes were discovered and reported in 1985. Atomic force microscope, which is similar conceptually to scanning tunneling microscope, that was also proposed and made, and it enabled imaging and manipulation at the nanoscale, and we can get the image. So STM AFM brought quite a revolution in imaging the nanomaterials or the materials which were at the nanoscale or even smaller. Then carbon nanotubes were proposed by the GIMA, and there's ACNT, SW and MWCNTs were discovered. That was in 1991. So some of you might have been born in that era. So now it is entering an era where you will be witnessing, or you are part of that journey even as a kid, but yet we are talking about journey of science and technology for whole human race. So then 1993 colloidal semiconductor quantum dot cadmium selenide based QBs were proposed and made, and they won the Nobel Prize in 2023. So 1993 they discovered, and 2023 they got the Nobel. So that is the journey for Nobel. Nobel is not got like how Trump wants. Right? So, and in our field, particularly in science and technology, it takes at least 2 decades of relentless, consistent, high quality research. And yes, it starts with something you discover very unique, novel, and you propose that, but then it is not, your journey doesn't end there. You have to explain to the world, convince to the world what it is, how it is, why it went there, how it is behaving like that. So all this, if you are not ready to do, many times we observe many things which are unique, novel, but then if we don't spend time in learning that why it is happening, how it is happening, we will not get information about it. But if we spend some time, we ourselves start getting some information that it be happening like that, and then you do some experimentation to prove your hypothesis, and then slowly that we built up that, and that is how the Nobel Prize in Science and Technology are awarded. So those who are getting now, they might have started 20, 30 years back their journey to discover something new. In 1994 to 1996, in that era, mesoporous silica, and then there are many candidates of mesoporous silica, MCM41, SBF15, there are some more also. So they were discovered and reported, and these are basically 3D nanostructured materials. So what sir was showing, zeolite. Zeolite is also one this type of mesoporous material, and it has and it is an engineered material. These are also engineered material, means their pore size and whole framework can be controlled. They can be made ion exchange ready. So you can introduce certain sites which will act as a site for ion exchange to occur. In zeolite, it is, as sir said, they are cation exchange. So we can exchange the cation, like sodium is there, then you replace sodium by various types of metal. And say for example, I want to use it as a ruthenium based catalyst, then I exchange sodium with ruthenium. So we know that ruthenium is normally in 3+ state and sodium is 1+. So many times the sites are not that much easily exchanged. We have to create the sites such a way that they are in vicinity of each other, so that multivalent cations can be replacing the monovalent sodium. So those type of designs they have created, and which is basically which groups we are choosing, how we are condensing. Yes, when these materials are made, we have mixed in proper composition the materials and given the conducive conditions. But how they are organized during the phase of reaction, it is not in our. It is materials they themselves decide based on the physical forces and environmental conditions which we have provided. Accordingly, they will be made. So many times this type of materials, even though they are they are very robust, they are known as self-assembled materials. We are just cooking it. putting everything, all the ingredients and necessary things, ions, many times templating ions we are put cation and we are going to put. So those are going to generate the, and this was by Mobil company, which is a oil company. It's a petroleum company, one of the world's largest petroleum company, Mobil. And particularly in terms of, maybe in terms of business, they might not be largest nowadays, but in terms of R&D, research and development generated for petroleum industry, Mobil is one of the largest, and their R&D produce this MCM41, SPA15 type of mesoporosilica, then zinc oxide nano wires. So these are similar to nanofibers, maybe a little more longer. And many times these nanowires are beyond nanoscale long. So only the diameter scale is nanometer. Length could be sometimes in micron or even millimeter, and they can be used for various applications, particularly piezoelectric nano generators and all. Then for nanoscale energy harvesting. Graphene, which is a very popular nowadays hero material. Lot of people are working on graphene or graphene derivatives. It's a carbon nanomaterial, carbon based nanomaterial. So it is one atom thick 2D carbon material. And graphene was discovered in 2004. So that means before that, graphene was not known as graphene and was not proposed to be used as graphene, but still its precursor was being used, that was graphite. So we were all using graphite for many of the applications which we are performing with graphene now, particularly the electrical and thermal applications which were done by graphite previously, now is being replaced by graphene. Graphene is doing more efficiently at a smaller scale. So portability you are getting. Say for example, you have you might be seeing this since last 10-15 years, the electronic gadgets, they are advertising that there is a liquid cooling. Liquid cooling is to cool the processor, where excessive processing power is needed for your applications, sometimes gaming. So suppose if I am buying a phone, and if it is capable of gaming, they know that the processor will be used exhaustively. It will generate a lot of heat, and that heat is going to be a killer for rest of the electronics. So they cannot leave that heating just where the person is going. એ લોકો એડવર્ટાઇઝમાં તો એવું ના લખે કે you have to play games only for 1 hour, then put it in refrigerator for cooling. So they give the cooling device inside. Now mobile phone is so tiny, so portable that you cannot put fans and everything practically there. So for that they give the cooling mechanism, that is called liquid cooling. They circulate the liquid inside, and liquid is also being circulated by temperature gradient difference. There is no practically motor or anything to run, and there is no inside peristaltic pump type mechanism to flow the liquid. It is flowing naturally by the temperature gradient. So cooler one and hotter one, the temperature difference. So that design they are making for cooling. Now if you have a graphene based suspension for cooling, it will be compared to simple liquid cooling. If liquid cooling they might be using previously, as because I work in this area, so previously they were using solvents, ethylene glycol they started, but slowly they changed it to water. So nowadays majority of these liquid cooling systems are containing water, because ethylene glycol is a big problem if it is leaked inside. It can catch fire also because it is an alcohol, and temperatures run near the hotter areas of your electronic gadgets are very high, mostly higher than 70-80 degrees. And your cooling system, effective cooling systems, bring them down below 50, normally in the range of good cell phones. If you are using and checking the temperature, they will be in the range of 42 to 45 degrees Celsius. So from 80, 85 to it is brought down to this temperature, and that work is done by cooling. So for that, this type of materials, they slowly invent and put. So slowly how nanomaterials adaptation into that is happening. That is what I am trying to tell. So they also got a Nobel Prize. This was relatively very quick. In 2004, the graphene was discovered or proposed, and then in 2010 they got the Nobel Prize for the first isolated 2D crystal of graphene. And then in 2004 to 5, in these 2 years, transition metal, dichalcogenides, molybdenum sulfide, layered transition metal compounds were discovered, and various groups were working. A lot many groups were working, and till today also there are many people working in this area. And these were mainly for this 2D electronics. Their band gaps were tunable and they are layered materials. Then topological insulators 2D and 3D were proposed in 2006. 2011 MXits were proposed, and nowadays you see after graphene and molybdenum sulfide type layered 2D materials, or even graphitic carbon nitride and those type of layered 2D materials. MXins are a very hot area of research, and they are showing a very good promise, similar to this carbides, nitrides, or graphene and other layered semiconductor type nanomaterials. So that is why these MXins are getting now. Then perovskite nanocrystals were proposed in 2012, and they are very highly luminescent. Quantum dots are prepared. They can be used for the LEDs and also for the solar cells. Their light harvesting efficiencies are much better compared to the conventional the photovoltaic based solars. So that is why they are slowly perovskite nanocrystals are going to replace. But currently at the scale which they are being produced is not enough to replace all the solar panels. But yes, efficiency wise they are showing a better result. The perovskite based materials. Black phosphorus, it is actually phosphorine, is again a networked material derived from phosphorus, just like graphene. So that is also again high mobility 2D semiconductor material with tunable band gap. And all these materials, they are in their pristine form, they have excellent properties. But another advantage with these materials, all this, that we can tune it, we can alter their structures, we can add certain groups. Many of these materials are layered materials, so inside their layer you can introduce other types of materials. Some of them not like zeolite or MCM and clays, that they have ion exchange capabilities, because majority of these are less hydrophilic, so their interiors are hydrophobic. So but still you can incorporate organic molecules, polymers, sheets, other type of sheets there, and we can create hybrid materials, and there also you can tune the properties. So that is why, and then in 2020s, Swisstronics, MOE 2D materials and all are coming, and they are also basically derivatives of graphene and other 2D materials. So this type of progress is happening in nanomaterials nowadays. So that is what I just wanted. So nanotechnology already affecting or showing its application in many areas: mechanical engineering, robotics, then quantum technology, we know all this. Then nanoelectronics, majority of the nanotechnology related. We are talking about the microchips being designed in India. For us, for our country, it is new, but otherwise, the whole world has already the processors of the size of 2 nanometer. Couple of companies already have claimed, but one of the company which is present in India, they have developed within India, but it is not an Indian company. Qualcomm has claimed it. So the 2 nanometer chip, now 2 nanometer size processor is very tiny, and in that processor there will be grooves. So normally these processors have grooves which are conductive, so they are actually wires. So it is a wired network on the processor. So it is 2 nanometer small, and in that, but whole processor is not 2 nanometer small. This 2 nanometer barrier is that they are talking about distance between two groups. So that much close wiring is there. Wiring means there are no practically wires. Conductive grooves are. So from which the electrical current will be passing. Electrical current is the carrier or messenger in all these processes. So they create a small square chip, you can see, which could be maybe in the size of 2 to 3 millimeter, in which 2 nanometer small grooves they were able to create. And that is why it is a big achievement, because that is created by a process called lithography. And the lithography device, the tip and the system which they are using, they themselves have some physical barriers not to go beyond certain size. So they are slowly modifying that lithography technique also. They are trying to go smaller and smaller, and with that they have created the grooves on this chip of 2 nanometer size apart from each other. So that means in a smaller size you can put more conductive network, and that means it is going to give you more processing power. So smaller chip, higher processing power. If you see your phones, if you are owning phones in, say, for example, 2014, so 2014 your phone might have certain gigahertz processing power. Now it will be multiplied by 2 to 3 times. In that time, around 800 MHz to 1 gigahertz, 1.2 gigahertz was very good processor. Now it has been almost 4 gigahertz processors are now available, 3.2 to 4 gigahertz processor. So this gigahertz means it is processing power in terms of frequency a processor can do, and to do that you require a smaller grooves through lithography. So nano electronics is one such area. Biotechnology, again, some of the drug delivery or at DNA level or at molecular level alteration of the biomaterials, and there are some synthetic viruses and all are being designed. They will be going to the biological system body, and they can repair the organs or can fight the disease condition, those type of. National security and defense, we know that even till today our country is looking for, if you look into DRDO's website or even on ISRO, they are looking for certain projects where researchers can produce radio frequency absorbents. So that is RF is being used by radars, and if you have radio frequency absorbents, they will be absorbing the radar signals. So practically they are asking for contributing towards stealth technology. We don't have our indigenous stealth technology. So the fourth or 4.5 generation aircraft which Tejas is not completely stealth. It is partially stealth. And even Rafale is also not completely stealth, it is also partially stealth. So stealthiness of a fighter aircraft or other things which your military installations also. Recently, I think 6 months back, I met a person. He was proposing a project to DRDO. Or DRDO had asked him to find out some researchers. They can produce a mat or a kind of net which is a radio frequency absorber. So if that is covered on, say, for your anti-aircraft gun or maybe missile launcher, then it will not be detected by the AWACS or whatever surveillance aircraft they are using, or even it can protect your installations from the satellite source. Because you might be remembering in Operation Sindhu, some of our positions of the S-400 and all were informed to Pakistan through Chinese satellites. Chinese satellites can still see, and if you move during the operation, they are seeing live that okay, this is the battery of S-400. Battery is whole setup. They call it battery in defense terminology. So battery of S-400 moving from Ambala to somewhere near border area or something, that will be detected continuously. But if it is covered under some kind of this radio frequency absorber nets, then many times it is yes, if it is detected optically, then they can observe. But normally first detection is always through radars and then they track. So that is why in national security and defense area requires lot of technological intervention from nanotechnology, and they are still looking for, because it is not ended. This research keeps on going. It is not anywhere that okay, now no need to do any research in this area. Always it is happening. Food and agriculture again, it is a big area where nanotechnology related interventions are being used. Particularly nano urea was in very much talk. Basically, nano urea is a nano suspension of urea. Now, if you all of you are chemistry students, or so being a chemist, you must be knowing urea is soluble, water soluble. And if it is anything is soluble, it is at molecular level. So it is already at Angstrom's level, and it is water soluble. So what they are making is actually nano suspension. So that means they are using not exactly urea. It is a nanoparticle constituting nitrogen and carbon. So it could be calcium cyanamide. One Chinese patent is on calcium cyanamide. Calcium cyanamide is not water soluble, not highly water soluble. So what they did, they nanonize, means they from the starting precursor level, they made the chemistry and make the nanoparticles of calcium cyanamide, and then they disperse in a water, and that can be sold as nano urea, because urea is nothing but basically a source of carbon and nitrogen for the plants. So, and out of that also carbon is not that much important. They want nitrogen, bioavailable nitrogen, fixable nitrogen. That is what plants are looking for, and that is provided by this. So if you find some other salt or some other compound which can be nanonized and can provide readily the nitrogen, and it is not detrimental to environment, means nitrate કેવું નહીં, because potassium nitrate તો સર show કર્યું, potassium nitrate as a fertilizer is already known. It is highly soluble, so you cannot make its nano suspension in water at least. So we have to make some nano suspension. Why they want nano suspension? Because urea is being used in excess. The way it is being administered by the end user. The end user is farmers. They are not educated. એ લોકોને ખબર નથી કે ભાઈ નેનો સ્કેલમાં જાની તો જરૂર, માઇક્રોગ્રામમાં યુરિયાની મતલબ નાઇટ્રોજનની જરૂર છે, and they are adding spraying worth kilos. So out of which only few the granules of urea will be dissolved and will be utilized by plant. Rest of that will be dissolved in water and it will be drained out from the farms. And that is excessive urea in that water is causing other environmental problem. If it goes to the ponds, it does excessive પ્લાન્ટ એટલે ઘણી બધી જગ્યાએ ખેડામાં તો બહુ પ્રોબ્લેમ, તળાવોમાં પેલી વનસ્પતિ ઉગી જાય, કુંભી કે એવું કંઈક કહે છે. So they are not easily, એને ન્યુટ્રિશન આમાંથી મળે છે પ્લાન્ટમાં, ખેતરમાં નાખેલા યુરિયા excessive nutrition છે. Naturally it might get some nutrition, but nature has any invasive species ને counter કરવાનું nature નું mechanism હોય જ. But this is disturbed when you use excessive urea, and that is why this problem is. So nano urea might be reduce the burden of usage of urea, and at the same time it is a smarter application, only the what it is required. The same is case of medicine and health. Many drugs which we are taking is in excess. So there is a term called effective dosage. Effective dosage for a particular disease condition is studied. The scientific number that say for example 1.2 micrograms of timolol maleate is required to fight glaucoma in certain hours, maybe 12 hours. So that much only is required. Now medicine is containing too much excess. Say for example eye drops of timolol maleate, if you are putting in your eyes, glaucoma એટલે જામર, slowly that is related to ocular blood pressure. એટલે આપણી આંખની અંદર જે blood pressure છે, that is actually aggravating that situation. So this drug is basically controlling the blood pressure of your eyes, inside the eyes. So that if it is administered through eye drops, out of few micrograms everything is drained off with your natural tears. The આપણું defense mechanism, it will not accept everything. Just you are, even if body considers everything foreign unless it is food. કારણ કે food માટે આપણું body designed. શેરડી ખાવ તો શેરડીના અંદરના પાર્ટ છોતરા સુધી એ ખાઈ જાવ તો it rejects. વધારે પડતી ખાઈ જાવ તો it rejects vigorously. That is allergic condition. Or similarly any drug it is given, body doesn't consider કે ભાઈ I am sick or I am ill, so I should take drug. એટલું બધું obedient ના હોય, it will reject. So that as soon as you add the eye drops, it will start producing tears excessive, and that will force out. So તમારું drug તો બહુ જરૂર હોય એટલું બી ના આવે. And that is why there if you design some nano material which is going to stay near the surface of eyes or interiors of the eyes and slowly releases the drug throughout the day, then it will. So for that you need to require some nano application. So there was one US based company, they did a project with us in 2012 to 14 in that period, where they were incorporating this type of drugs in nanoform in the lenses, eye lenses, optical lenses which people wear. So in those lenses we can incorporate the drug, and then if you wear that lens for full 8 hours, it is going to release slowly the effective dosage amount for these 8 hours. And similarly in the night if you want to remove, you can remove again in the morning. So that is continuously required dosage amount you are providing for few days till you are under medication, and then medical expert means doctor will evaluate, and then they can recommend further or they can stop from that. So that is how then that nano drug means timolol maleate only we use, but we converted it into its nano form and then encapsulated into a carrier which was slowly released. So those type of things is required energy and environment, particularly energy storage. A lot of nanomaterial intervention is happening. As I said that in renewable energy case where perovskite and other new novel nanomaterials which are coming for better energy harvesting and for that application. Environment again this pollutants what we are talking, even uh, this urea thing. Urea is a very small molecule. It is very difficult to degrade. But other pesticides and other materials, chemicals which are being used by farmers in the farms, or which are being used by us, like what Gandhi sir was telling about the textile companies problem. So textile companies are using, apart from these salts are still manageable. Yes, beyond certain concentration, they are also a big environmental menace. But normally dyes, the organic molecules, nitro, azo, all these groups, phthalic, so they are big problems for the environment, and they need to be degraded. So for degradation, there are several routes. I mean, there are several stages: primary, secondary, and tertiary uh, treatments. Wastewater treatment processes are there. In tertiary, there is a process called advanced oxidation process. That is basically, it oxidizes this type of pollutants, persistent pollutants. And they are normally not in very large quantity after first two set of wastewater treatment. First two stage and take care of that, and still they are again in the range of several hundred ppm, around 100 to 200 ppm, not more. But that also is then detrimental, so that needs to be degraded. For that, nanophoto-catalysts are coming, which are normally using solar energy, because they are photocatalysts, so they can take solar energy and degrade this material. So in the pond, if you disperse this nanocatalyst, which is normally a nano semiconductor materials such as titania, sedeno, or copper doped titania or iron doped titania, those type of materials. And if you spread that in suspended in this type of tanks which are made for treatment for the ponds, there it will be doing the photocatalytic degradation of this material. It works with all the chemicals, not only dyes, even pesticides, other solvents, and whatever is coming to that. So at this source of pollution, the companies should, their effluent treatment plants also can incorporate that. Then in aerospace, some of that we already talked, and in artificial intelligence now it is coming. Then advanced materials and textiles, there are also lots of this type of material, the radio frequency absorbing particles incorporated, they wanted in textile only. So textile incorporated with, so if I create a, say for example, nanofibers of this type of material, and then blend it with the textile fibers, and when these textile mats or the carpets or covers, or if they are made, they will be having this radio frequency absorption capacity. So this type of advanced materials, not only for that, for various other applications are also being prepared, and it is used. Information technology. So these are the main areas where we can see the nanotechnology contributing towards, or in terms of applications. This is just to show the scale example. This is graphite, the pencil lead, and this how it looks at the millimeter to micron scale, the graphite. This is millimeter, micron to nanometer scale graphite diagram. So this is obviously, this is scanning electron microscopy, and this is also, and this one is not same image, but this is at 10 picometer range, and this is somewhere into this is produced by the scanning electron, atomic force microscope. And there you can see the hexagonal pattern also for this graphite or graphite. And this is going almost up to, and if you have some kind of modification on this, say if you do the convert it into graphene oxide, then it will have COH or hydroxyl groups there, or sometimes even epoxide groups are there. So these, because of the oxidation of graphene, will get converted to corresponding oxidized form. So that all will be there and it can be observed by this, and if you do some kind of chemistry over there, carboxylic group to something else, you S with ester linkage, you if you connect something else, so those things you can observe. Now, unique features of nanomaterials, why they are so hot in terms of their application, because they have a dominant role of surface atoms. 60% of the atoms are on the surface for 2 nanometer sphere. So if a sphere is of 2 nanometer, out of its total volume, 60% is on the surfaces. So their surface role becomes very prominent, and it will start showing the size effects. Many of the physical properties it will be. So basically, say for example, optics, if we are talking, then we are the wavelength which we are seeing the material that is visible, or even ultraviolet, they are in the range of 100 to 180, 200 nanometers range, the ultraviolet. These materials are far smaller than that. So that is why they will be showing, or they will be exhibiting some novel properties which optically we are not observing from in terms of bulk materials. Then there will be dangling and unsatisfied bonds. The defects will become more prominent. The surface vacancy clusters are there. We are making a material, but there will be defects, so there will be some vacancy clusters or voids are there. So they will be also becoming prominent in terms of affecting the overall property. Surface energy will be modified. Surface and atomic electronic states are also modified. So these features contribute toward the novel properties exhibited by the nanomaterials, and that alter the interaction of nanomaterials with the other bulk materials where you are using. So if you say, for example, lot of people, if you see the nanomaterials general application, like what Gandhi sir was telling, that not very high-fi, but routine application, say for example, if in concrete admixture, concrete banana slurry, in that if you mix nanomaterial, then what it will do, so that it alters its compressive strength, its settling time. So settling time is a big parameter all the civil engineers are concerned with. How quickly the concrete is settling or how much time it takes, and if they want to alter it many times. If it settles very quickly, then it gets compacted very quickly, and that is desirable. It will weaken the overall construction process. So they want that, but in conventional materials there is a problem that they exert lot of heat while compacting, because there is a chemistry inside going on to this bonding. So internal binding is exothermic process, and that is why when we construct the house, we cool it from outside by spraying water. જેના ઘરમાં બહુ ક્રેક પડે ત્યારે તરત કે આમાં ફિલ્ટરે પાણી બધું છંટાયું નથી. So that is because of this. But if you have a certain nanomaterials which will avoid, means they make compaction but will not have that conventional chemical processes, exothermic processes, then heat release will be very less and still the compaction will be quicker. So that is desirable by civil engineers. So that is why many people add different nanomaterials. Some go to very exotic nanomaterials also, like carbon nanotubes, and some settle with simpler nanomaterials such as nanosilica. Nanosilica is easily available in large quantity compared to other nano. Carbon nanotubes are very expensive. If you go for its 1 gram price is very high. So one person in GTU, Gujarat Technological University, he was pursuing PhD in applied mechanics, I guess, and his background was civil engineering, and he used carbon nanotubes in the concrete. And initially, why I was knowing, because I was in the panel of that PhD candidate at the same time first batch of carbon nanotube I had given. So he came to us and he said, I am pursuing PhD in this, I want some carbon nanomaterials. So at that time also we had talked briefly about the cost. Carbon nanotubes are very expensive. If you see, I think I don't remember correctly, but currently also it will be somewhere close to 10 to 12,000 per gram of carbon. So, but yes, he got a sample for free. Another time also, I think through Manoj sir, he got a sample for free from SP University Material Science Department. So he had a good amount of carbon nanotube available with him freely, and with that he could construct some kind of small blocks which they designed, cement, the concrete. And then he studied all the conventional parameters, compressive strength, settling time, this, that, and everywhere, majority of the parameters, he got excellent results because of the carbon nanotube. Then when he was presenting last RBC Doctoral Progress Committee, he showed that result, and one of the conventional civil engineer was also a part of the expert panel. He said, if I want to make 1 meter by 1 meter cube of this material, concrete, with your nano additive, how much it would cost? So then he calculated something, and he said like somewhere close to 1 lakh. So he said, then how can you justify where the cost will meet and this? And then, as it happens, many of you, if you are pursuing PhD, you are knowing that your guide wants you to finish the PhD quickly. So his madam, he was the lady, and she was she was getting transfer, so she wanted him to complete PhD quickly. So then I said that send the candidate out, and then we will discuss. And then I said that if he can propose that this is for high-end application, say for example, if I want to construct a bunker to protect top leadership or certain crucial military establishment or even nuclear plants, then this cost can be justified. Or so you write like this, that this application is good, but it is only serving this type of purpose, then everything is served. Then madam was very happy, obviously, then he got the PhD. So this happens with nanomaterials, that where you want to use how much quantity, still cost barrier is still there. Still, a lot of field might get benefit of from the intervention of nanomaterial, but still cost is the biggest imperative that they have to look into. Say for example, oil recovery. Enhanced oil recovery is a field where nanomaterials can enhance the oil recovery. But the recovered oil, if you process, are you going to gain so much extra profit that you can compensate the expenditure while you added the nanomaterial into the recovery fluid? Because recovery fluid is used in millions of liters for the flooding in the oil wells. Oil wells are kilometers deep, so it requires a lot of fluid which pushes that oil out. In that, if you add certain nanomaterials, it might improve the recovery by certain percentage. Say maybe without that you are getting 27% sweep efficiency. That might go to 37 or 40%. So you get 10-12% extra oil per sweep. But is it going to justify the cost what you are adding into thousands of liters or millions of liters of that flooding fluid? So that is how this is still changing the dynamics. But slowly, yes, if you have materials, nanomaterials produced at a lower cost in larger quantity to meet the demand of the area where it is being applied, then so nanomaterials normally, simplest is soft and hard nanomaterials. Many times people think that how do you measure the softness or hardness, but basically another term people use it is inorganic and organic. But in inorganic also, these carbon nanomaterials are, it is debatable whether to term them organic or inorganic. But they are hard nanomaterials. They are very robust. They have all the physical parameters, tensile strength and all this, Young's modulus and all are very good. And they can be used for high-end applications where they chemically also very inert. So they don't get easily oxidized or what we call biomineralized by microorganism and all. They are very robust. Soft nanomaterials are normally polymeric nanomaterials or dendrimers type or metal organic frameworks type. They are basically made for us and all, and layer to layer we have constructed them. And this type of surfactants and liposomes again, they are made based on self-assembly concept. So surfactant is a single molecule, but when it is added into a suitable medium liquid, then it will construct a micelle. And that micelle is a nano material or nano constituent. So these are hard nanomaterials, these are soft. Soft nanomaterials are normally this type of materials, polyethylene glycol could be ligands, and then it is constructed inside we have incorporated the drugs. These are liposomes, polymeric nanoparticles, dendrimers. Dendrimers are growing like tree, and then their pores, several generations are there, first, second, third. So third generation dendrimer will be a very vast 3D network having too many functional groups on the periphery, and they can be used for various applications. In case of organic, they are normally organic. Even 2D material, they are porous oxides or dendrimers. And in hard nanomaterials, normally layered materials or metal oxide nanoparticles, single spherical particles, quantum dots, and they have various applications. So this type of two clear-cut distinctions are there. But nowadays the era is of composite. So these are also hybridized. You have a metal nanoparticle, say for example silver or gold, and on that then again we can construct the polymeric layer can be put with different type of desired functional group, or even dendrimers can be constituted. A DNA can be bound on the gold surface and then it can be delivered to the inside, or drug molecules can be entered. So this concept normally for self-assembly very widely used. These functional materials are incorporated and put into a thin film or coating micelles. They can be constructed in form of a helical or polymer structures, and then they are used for various applications. And metal nanoparticles, we know that they start with the, normally if we go by the which approach? Bottom up. Top down approach, it is already existing. Say for example calcium carbonate nanoparticles, I want to be used it as a to make certain materials or paint or rubber or something. I have use it as a ingredient, structural ingredient. Then I can make it start from the top down approach also. I can take the rocks of calcium carbonate and grind it up to nanoscale, which is beyond submicron range, means 1 micron beyond it is very difficult to grind a material to nanoscale. It is usually not easy. So then there are other destructive techniques, laser ablation and all, but they are very expensive. So normally top down approach for creating very small nanomaterials is not that easy. But yes, in your application, say for example, I am adding calcium carbonate in rubber. So in rubber, if 800 nanometer or 1 micron calcium carbonate is sufficient to give the whatever structural properties they want, opacity and other things, then I don't need to go all the way up to 100 nano. So in that case, top down works because it is easier to produce in large scale, top down. based materials. So that works, but this is an example where metal and metal oxide nanoparticles are started from the their precursors. So it is a bottom-up approach, and then we create nanoparticles. Normally, if they are unprotected, they have tendency to agglomerate, and with Oswald lightning and or they might either form cluster or they grow bigger. If only metal nanoparticles are there. If they are metal chalcogenide nanoparticles, then they will form cluster or agglomerates. And to avoid that, normally stabilization is carried out by ligands or polymers or surfactants, which is coated on that. So they are directly suspended into the liquids where these are already there. So they will go to their surface and protect. And once their coating happens, they will be practically detached from agglomerate. So they will not get agglomerate very quickly. Yes, many times these coatings are in situ, and they are they tend to they are labile. They many times fall apart and again form, fall apart and again form. During that process, if they get enough time, they may start getting agglomeration. So that optimization needs to be carried out, which type of surfactant you are using and how quickly it is forming a kind of coating on that your metal oxide or metal nanoparticle surfaces. And another approach is once you synthesize nanoparticles and then to permanently coat certain type of coating, nano coating, which will not allow this to bind again. So, such as say for example, any metal oxide has tendency to carboxylate containing groups. So if I use oleic acid coated on iron oxide nanoparticles, then it will be a permanent coating. It will not be detached, because with iron hydroxide defects on the iron oxide nanoparticle, it will go and bind permanently. So oleic acid will be bound like this and it will not be falling apart. So there will be a permanent coating. It will not allow the nanoparticles to agglomerate, and the size control will be done. These all exercises basically done to control the size, because as soon as if you allow them to agglomerate, they will go out of nano domain and it will be in the micron size or sometimes even larger. Depends how long you allow them to agglomerate. So that is why now we are moving to carbon nanostructures. These are very fascinating materials because of their various properties. Some of them are not very easy to what we call the synthesize them with control. Like if you are trying to synthesize fullerene, you end up with several other things also, and then their separation is a big challenge. Like you get carbon nanotubes also, some graphene sheets also, then you have to separate graphene sheets, fullerene, carbon nanotube. And that separation is a big challenge, and that is why many times these carbon nanomaterials are very expensive. And still that is why graphite and graphene are more preferred compared to other carbon nanomaterials, despite them having better or equal properties. So this is graphene nanostructure. Basically, it is sp2 hybridized carbon network, and how it is folded, that depends. If you roll like this, like that, accordingly their geometry will be changing, and that is going to affect the transport of current or transport of electron from these sheets, and that affects the overall electrical conductivity. So carbon nanotubes also in general, depending on their geometry, how they are folded, they will have different types of electrical conductivity. And graphene sheets, yes, if they are not having too many defects, if they are pristine, they will have very good electrical conductivity, single graphene sheet. And if they are converted to graphene oxide, CO, what people call it, that is having a problem with the conductivity. Electrical conductivity is not there, but graphene oxide is, if you are trying to synthesize or produce graphene using any chemical method, graphene oxide is easier made compared to pure pristine graphene. And that is why many applications are carried out with graphene oxide, and in majority of the things it is similar to that, because it also has a sheet type structure. Little more curling and defects are there, but still it has a similar type of structure. Plus, apart from electrical conductivity, majority of the physical properties of graphene is translated or replicated into graphene oxide. So graphene oxide is cheaper alternative to graphene, and many times chemists use that for as a catalytic support or to anchor any other molecules there. So this is how. So this is electrical conductor. But if you have this type of zigzag type of, that is electrical insulation. So armchair or zigzag, that is going to determine the. So in armchair you see this is like that, and in zigzag it is just like hydrocarbon chain. So that is this is zigzag geometry, and this is armchair, and that difference is there, and it is based on how it is folded. So when it was in form of a open sheet, then it is so this graphene is actually precursor to carbon nanotube. And if you provide sufficient amount of energy, it will be folded. So during the process of producing graphene, many times we produce carbon nanotubes also. And this is soft nanomaterials, micelles and reverse micelles. Basically, micelles are formed in aqueous medium. This is non-aqueous medium. You will have the reverse micelle. In that, polar group is in the interior, and external periphery is containing the non-polar groups or hydrocarbon chains normally, and that is compatible to oil. So micelle and reverse micelle, and they are used for various solubilization in various medium to carry the material. But micelle and reverse micelles are always dynamic. They are forming and dissociating very quickly, and that is in the normally in the milliseconds or even smaller lesser times. So they are very quick to form, and so it is practically in the time scale in which we are first forming and applying or doing any reaction. It is sufficiently quick to show the result, but there in some cases if they are too slow to form, and then you will see their effect in the undesired effects will be seen. This is basically bilayer sheet of this type of surfactant molecules. In the body it can be seen, and in liposome. So these are basically lipid, and then these phosphate groups are there in our body, the natural system. But to mimic that also, by mimicking that, lot of other bilayer sheets and liposomal candidates are synthesized, and they are used for various applications, particularly mainly for drug delivery and all. Then applications, spatial applications, basically this is a kind of summary sheets where 2D nanomaterials, quantum dots, emexins, nanoparticles which are used for catalysts and composites and biomedical applications are shown in a single sheet. So this comprises almost all the applications, but some specific applications. Here carbon nanotubes were used as wires to conduct the electricity, and they are very tiny, so they give you advantage of portability. So this is nanotube is spreading over that, and this is source electrode, drain electrode. So basically they have created a small transistor, field effect transistor here with carbon nanotube, and the length is 1 micron, thickness is in nanoscale. So this is one example, and this type of structures are used practically nowadays for electronic applications. This is for drug delivery, a small cheap scale, and that it has a kind of tiny needles, so that it will be sticking to the skin, and from that it will be delivering the drug. So it is a patch you can fix, and it is very tiny. And some of these are having multiple layers. One layer is comprising the drug, another is drug delivery part which is going to your skin. So it is basically designed for transdermal drug delivery in terms of pharmacy language. And upper layer is normally having circuit, so that it can be controlled by various wearable and other devices through your mobile and all. So you can give the stimuli as and when you require. Like, for example, if you have a patch against diabetes, so at a particular time interval you need that after the lunch or something. So that time you can trigger with your device, with your wearable wristwatch or mobile. You click it and then that electronic chip over the layer that will activate and it will push that. So this is how the drug delivery is done. Yes, these dendrimers, hyperstar or brush type structures are synthesized and they can be used for using a drug carrier, and even they can be used to deliver the gene for the genetical modification or gene repair. A disease gene can be replaced, and so this type of porous structures are created with organic dendrimers with metal parts are there. So it is kind of hybrid, and they are used mainly for CO2 capture. This type of applications are there. This is a progress of cancer drug delivery. Liposomal delivery was known in even in 1965, but that time candidates were mostly derived from natural material. Nowadays, synthetic liposomes are also there, but then dendrimers were used, doxil, and then currently to around 2015, they have the liposomal candidate with special modified surfaces, and they have special binders which can go for targeted delivery. So they will bind only with the cancer cells, other cells are not affected, and drug will be released only in the vicinity of the cancers, not throughout them. So that is how targeted drug delivery, and nowadays this is the era of nanotheranostics. Theranostic term is basically a hybrid word of therapeutics and diagnostics. So basically it does both. It diagnoses first when you insert into the diseased body or system. It will first diagnose where these tumor cells are located. When and it is having special groups which have a binding with maybe glutathione or something, because cancer cell has tendency to produce excessive glutathione or something other enzymes also. So it will go and seek for that. If that is there, then it will bind. And once binding happens, it will be show the signal in terms of fluorescence or something. When you do that imaging, it will glow there. So maximum glowing means there you have a cancerous area. Then you located the region. So diagnosis part is done. Then comes the therapeutics. So similar material will be, once it is binding there, then it is capable of delivering drug also. So it is carrying drug also. So in the periphery they have normally the receptors and binders and even the fluorescent probes which will be doing all the diagnostic and binding part, targeting and binding. And in the cavity, if they are porous like liposomes and all, they will be carrying the drug that will be released there. So this is how and that is why in recent years you might find that the medication for cancer treatment has been, it is now widely available, easily available. The success rate has also a little bit improved. Particularly in developed countries, it is very rare you see. Recoveries are very, very common from cancer, certain cancers. So that is also happening in our country. Also, recovery rate is good, but still the people getting cancer is also rapidly increasing. So you will not see in terms of number much improvement, but in past lesser cases where cancers were reported, but fatality was very high. Now fatality has little bit reduced, but the number of cases is on the rise. So that is how this in nano era maybe will have this type of drugs, and some of these are already being tested for clinical trials. As we know that in drugs and all, again the testing cycle is very vast. It takes around 7 to 8 years for a drug to come into market. So that is still not very commonly available. Some of the advanced drug designs which were drug delivery system by certain leading pharmaceutical companies is already available. This is thin film solar cell on polymeric kept on this multi-layer. So layer by layer assembly, and then you make it a flexible solar cell. Nowadays it is commercially available. You can also have it is a foldable complete. You can fold it and make it like it is like ફરવા સેવગંજી લઈને ગયા હોય એમ જઈ શકાય. Vehicle you can cover it and it will capture the sunlight, run your gadgets, some of the devices, even mobile and tablets and all. And some of the larger capacity one can even run your cooking devices also, electrical cooking devices. So these type of things are now available. Implantable sensors are there. So they will be having a microchip and then report back to the gadget, and it will monitor the blood pressure and wirelessly, and it will be reported back to you or the person or doctor. This is retina implants, where the implants can be artificially assisting in the visualization. So this type of things were reported in way back in 2003. Many of these things you will see are actually existing today. They are already converted into technology. So yes, it takes time. Normally a decade or 10 to 15 years period is there. But if a kind of rigorous research is carried out relentless behind that, then those technologies are actually become reality, and then they can be used for the. So this is solar leaf-like model. Leaf has very high efficiency. So now people are trying to biomimic the energy harvesting, because this has reached only up to 28, 20, 30% barrier recently closed by Paros, 36% they've gone. But that is still far lesser than biological application. Nano coatings are also being used. They are having a very thickness of nanometers, and they can be used for various applications. Basically, functional coating or self-assembled nanophase coating. There are mainly two types. And then implantable materials are coated with nano particles of nano coatings. They will help in producing better surface properties in some time. In case of implants, they will be helping the for catheters, and then they will make it biocompatible better. And in some cases, if they are used for implants which are used in body, they will be helping in generating tissues faster, and the bonding will be better. So say for broken bone, if an implant is fitted, if it is coated with a nanomaterial which is assisting or which is accelerating the tissue and binding with the bone better, then it will be very quickly adjusted or what we call the acclimatized in that biological environment. And some of the other functional coatings are for self-cleaning and defouling. They are having a very good feel. They are antibacterial, anti-corrosive. And this type of applications, some of the nanomaterials you see in terms of coating are widely used in tiles industries. The tiles are having now abrasion-resistant coatings, and they are nano coating. Majority of them in India are still imported from China. Most of them chemically are using silence as the materials. So silence bind with the earthen part of your tiles, because tiles is also produced from the silica type earthen material, ceramic material. So it binds naturally with that silence, and then it is a permanent coating, and then it imparts abrasion resistance, a glossy feel, many other properties, whatever you require for the tiles. So these materials are mostly coming from China. Some of the companies are trying to make in India, but that is also a kind of formulation only. The silence they are not synthesizing, because synthesis of silence requires to work with chlorosilane, and their handling is problem because of the pollution norms very strict here. Halogenated silence are problem. So those things are coming even for automotive market. These are now becoming very. So you have all these polishing things. There is one for pure polymer based, organic polymer based, epoxy and other polymer coatings are there, Teflon based. But others are silane based coatings, which are not very long lasting, but they are giving a very good feel. Ceramic coating, few years after you have to do it again. But they are very good. They give the corrosive property also to the body of your car and automobile. So that is also area where coating and all is becoming very popular. So this is it from my side. I will end here. And any question if you have in this.
We sincerely thank Dr. Atindra Shukla sir for his insightful lecture on nanotechnology and nanomaterial, which greatly inspired and enriched all the participants.
What truly stands out was your powerful message that innovation alone is not enough. We must deeply understand what we create, why it behaves the way it does, and dedicate time to truly learning science behind it.
As a token of love and respect, I would like to invite Dr. Rohit sir to present memento and letter of appreciation to Dr. Atindra Shukla sir.
Thank you, sir. Ladies and gentlemen, we are now taking a lunch break. Our delicious lunch is ready for you in the dining area of the ISTAR.